Hello, my name is Atsushi KANEKO from Shinshu University, Japan. I will start my presentation entitled One-Piece 3D Printed Legs Using Compliant Mechanisms that Produce Effective Propulsive Force for Hexapod Robot Locomotion. We propose a leg design method for a hexapod robot that increases the propulsive force by kicking the ground using elastic force. Almost all parts of the leg can be 3D printed in one piece. Experiments are conducted to compare the proposed leg with deteriorated types. As shown in this video, some of the results indicate that the proposed leg improves the locomotion speed. Let me explain the research background on legged robots and the objective of this study. The one-dimensional elasticity of the legs has been mainly designed to improve locomotion performance. First, previous studies on animals simplified the entire legs into a single spring, as shown here. Then, they found that the animals can generate efficient locomotion by utilizing the elasticity of this spring. Let me call this spring stiffness the vertical stiffness in this presentation. Robots with high locomotion performance such as our Hex were developed by adjusting the vertical stiffness closer to that of the animal. In contrast to these studies, we aimed to develop a leg that increases propulsive force using elastic force with low fabrication cost. Now I will explain how to achieve it. I mean proposed method. The concept is to increase the propulsive force by kicking the ground strongly backward using the elastic energy stored in the legs. We will explain this method using the locomotion of our hexapod robot. Two candidate design requirements were devised to increase the propulsive force. The first is that the legs should store a larger amount of elastic energy when the ground reaction force is applied to kick strongly. The second is that the toe should project forward at the moment to generate backward elastic force. The amount of this displacement was defined as forward displacement. The working hypothesis is that these design requirements contribute to increasing robot speed is tested in the experimental part. Now let me move on to how to model a leg to conduct physical simulation. The leg consists of an I-shaped beam and C-shaped part, and a rubber part is attached to the toe to reduce slippage during the kicking motion. The entire leg is modeled as torsion and linear springs. The robot rotates its legs in this direction during locomotion. A static simulation is performed to reproduce the deformation at the moment when the leg is inclined 68 degrees with respect to the ground. This is because we assume that the contact point shifts to the rubber part at this angle. The leg angle when the leg contacts the ground is called the angle of attack, which is one of the parameters of legged robots. In other words, the simulation best reproduces the leg deformation when the angle of attack is 68 degrees. We then combine the simulation with multi-objective optimization. We use the 3D CAD system called Rhinoceros and its plugins for the simulation and optimization. This platform contains a physical simulator which simulates consequent deformation and genetic algorithm for the optimization. This is an example of a Rhinoceros simulation. The following three objective functions were set in the optimization. The first is to maximize the amount of elastic energy stored after deformation. The second is to maximize the forward displacement. The third is to make the vertical stiffness of the legs similar to that of an animal. The following three values were set as optimization variables. First, the stiffness of the torsion springs in the I-shaped part. Second, the stiffness of the torsion springs in the C-shaped part. And third, the I-shaped part arrangement. Candidates for arrangement of the I-shaped part are represented by the green lines. Based on the simulation and optimization, we fabricated three types of legs: the optimized leg, and two detailed types for comparison. The whole leg except for the rubber part was 3D printed in one piece. The right plot shows each type's elastic energy and forward displacement obtained by simulation. The leg fabricated to achieve the shape and stiffness obtained by optimization is named large. It is because the optimized leg has larger elastic energy and forward displacement in the plot. The detailed types of legs are similarly named medium and small. Here I will show you the prototype Hexapod robot. 6 DC motors were fixed to the body, as shown in the left figure. Each leg was rotated using a single motor to realize locomotion, as shown in the right video. The 3 green motors and 3 red motors are synchronized respectively. The robot travels using a tripod gate, which is a gate commonly seen in insects. We implemented a control to adjust and specify the angle of attack to study the effect of leg deformation and angle of attack on locomotion performance. The angle of attack affects locomotion performance. Each motor has 2 phases in a cycle, the rotation phase and the pause phase. When the leg rotates to the specified angle, theta AOA, the motor pauses for T pause. We assume that the leg will touch the ground during the pause phase, and the specified angle theta AOA will determine the angle of attack. Now I will describe the experimental setup. We conducted the experiment to investigate differences in locomotion speed by varying the leg type and the angle of attack. Here are videos of the experiment when the angle of attack is 60 degrees. The robot traveled for 5 cycles in each locomotion experiment. The locomotion experiment was repeated 3 times for each setting. Then, the mean and standard deviation of the locomotion speeds were calculated. Before summarizing the results, let me explain the analysis of the time variation of speed. The graph shows the change in locomotion speed in the experiment on the previous slide. The period during which one motor group pauses is shown as green in the plot. Near that period, the legs made contact with the ground, resulting in a decrease in speed. When the motor group started to rotate again, the legs kicked the ground, then the speed increased. The moment when the speed is the lowest near the pause period is defined as the beginning of a kick. Meanwhile, the moment when the speed is the highest during the motor rotation is defined as the end of the kick. The mean and standard deviation of the speed difference before and after these kicks were calculated. Now I will show you the experimental results. The graph shows the average speed and the speed difference before and after the kick. The rate frame indicates the angle of attack of 68 degrees, which is the setting in the optimization, and the angle of attack of 60 degrees. In the red frame, large, medium, and small tend to show higher average speeds and larger speed differences in that order. The result indicates that the elastic energy in the legs and forward displacement may have increased the propulsive force. Finally, I will conclude this presentation. We proposed a design method for one-piece 3D printed robot legs to increase propulsive force by kicking the ground using elastic force. We demonstrated the function of kicking the ground in experiments using a hexapod robot. This study suggests that soft robotic parts with various functions, such as hands and arms, can be designed using continuous deformation and one-piece 3D printed parts. This study was supported by following grants. Thank you for listening.